Hello everyone. Today I am going to talk to you about a very important technique for solid state characterization called as differential scanning calorimetry, in short, which is also called as DSC. DSC is one of the most important and common technique that is used for solid state characterization of pharmaceuticals. We are going to discuss our talk in the flow that is given here. We'll first talk about the importance of solid state pharmaceutics. What are its biopharmaceutical implications? General analytical techniques that are used for solid state characterization. What is DSC and types of DSC? What DSC can measure? The calibration of the equipment, sample preparation related parameters, applications of DSC in the pharmaceutical sciences, and finally we'll talk about the summary so that we can understand in a nutshell what are the applications of DSC in the field of pharmaceuticals. Starting with the importance of solid state pharmaceutics, as the name indicates, the impact of solid state on the field of pharmaceutics is covered by the term solid state pharmaceutics. As we all know, most of the active pharmaceutical ingredients are marketed as solid powders, which means they are in the solid state, and their solid state properties hence are going to be very important for their performance. Solid state properties can be classified into three categories. Molecular level properties are associated with the arrangement of individual molecules in the crystal lattice or in the solid form. Solid form, as we know, is the condensed state of matter as against the liquid or the gaseous state, where the molecules are moving randomly and ceaselessly. In the solid states, the molecules are held together by intermolecular interactions, and it can lead to crystalline state, solvated state, or the amorphous form. These are the instruments that are used for the characterization of the molecular level of solid state. The next level is called as the particle level and includes properties like particle size, crystal habit, and surface characteristics, and these are the means by which we characterize the particle level properties. The third level is called as the bulk level, which is contributed by a group of particles and includes properties like bulk density, compressibility, flow properties, and cohesivity. And these are some of the parameters that are used to define the bulk state of the solid state. The biopharmaceutical implications of solid state are immense, and they can impact the thermodynamic properties, kinetic properties like dissolution, stability, and the rate of solid state reactions, mechanical properties like compactability of the tablets, packing properties like the true density, refractive index, etc., surface properties like surface free energy and habit, and the free energy is known to govern the properties like solubility, reactivity, and compactability. Higher the surface free energy of a solid form, more would be its solubility and reactivity. As is evident from this slide, the solid state properties can impact a whole lot of properties that are relevant for the pharmaceuticals. That is why it becomes very, very important to characterize the solid state properties using appropriate techniques. These are the techniques that are used in journal for solid state characterization. Microscopy like optical microscopy and cross polarized microscope. Thermal techniques like DSC, solution calorimetry, TGA, and hot stage microscopy. Spectroscopic techniques like FTIR, NIR, Raman, solid state NMR, dielectric spectroscopy. Crystallographic techniques like XRPD, single crystal XRD, small angle X-ray scattering, and then these days the computational techniques are also increasingly being used for the solid state characterization. The emphasis of today's talk is going to be on differential scanning calorimetry, which is a type of thermal technique for solid state characterization. Now let us try to understand what is a DSC. A calorimeter is an instrument that measures heat that is going into or coming out of a sample. Differential calorimeter is a instrument that measures heat of a sample relative to that of a reference sample. And a differential scanning calorimeter measures the heat difference between the sample and the reference while heating the sample at a linear temperature ramp. DSC is predominantly used in the non-isothermal mode, although there are applications of DSC that have been reported at the isothermal mode also. Non-isothermal mode means that we are not carrying out the experiment at a fixed temperature. Rather, the temperature is continuously changing. It is either being heated or the sample is being cooled. That is called as the non-isothermal mode. There are two types of DSC that are available commercially. The first one is called as a heat flux DSC, while the second one is called as the power compensated DSC. It is also sometimes called as heat flow DSC. The construction of these two types are completely different, and we will try to understand with the help of these diagrams what are the significant differences between the construction of a heat flux and a power compensated DSC. Heat flux DSC consists of a single furnace or a single heating source, and there is a sample cell holder and there is a reference cell. Enthalpy or heat capacity changes in the sample cause a difference in its temperature relative to the reference, which means the events that are going in the sample lead to a difference in the temperature delta T with respect to the reference. This temperature difference is recorded in the heat flux DSC and related to the enthalpy change in the sample using a calibration experiment, which means the instrument has already been calibrated by the manufacturer so that they are able to correlate or convert the temperature differences into the enthalpy changes that are taking place in the sample. In contrast to that, power compensated DSC has two individual furnaces or two individual heaters, one for the sample and the other one for the reference. The temperature of the sample and reference are made identical by varying the power input to the two furnaces, and the energy required to do this is a measure of the enthalpy or heat capacity changes that are taking place in the sample relative to that of the reference. So what is done is that whenever there is a heat change taking place in the sample, the power is compensated by the instrument so as to bring the temperature of the sample to the same value as the reference. So this power that is consumed is then converted to calculate the heat capacity changes or the enthalpy changes. Industrially and in the academic institutions that are dealing with the pharmaceuticals, heat flux instruments are more commonly used. The DSC can measure the following events: melting point and boiling point of the sample, heat or enthalpy of the reactions, specific heat capacity of the sample, polymorphic transitions, glass transition temperature of the amorphous form, recrystallization time and temperature of the amorphous form, percent crystallinity, and molecular mobility of the amorphous form. There are two types of events that are shown in the DSC: endothermic events and exothermic events. And these can be understood by looking at the direction in which the event happened. Most commonly in the DSCs, the endothermic events are shown as a downward shift in the heating curve, while the exothermic events are shown by an upward shift in the heating curve. Some of the endothermic events that are important for pharmaceuticals include solvent loss, melting point, enantiotropic polymorphic transition, and enthalpy relaxation in the amorphous samples. While the important exothermic events include recrystallization of the amorphous form, or as such, recrystallization of one crystalline form to another crystalline form, monotropic polymorphic transitions are also associated with the exothermic change. Just for the benefit of the understanding, enthalpy is heat energy that is absorbed or evolved during a chemical reaction, and specific heat capacity is defined as the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 Kelvin temperature. The DSC instrument, as like all other instruments, need to be calibrated before use, and these are the protocols that are used for the calibration of the DSC. We are not going to get into the full details, but just as an example, the calibration of the temperature and heat flow can be done using standard samples of mercury, water, indium, and zinc. The baseline of the heating curve can be calibrated using sapphire as the sample. Similarly, heat capacity can be calibrated using sapphire. High purity standards of these samples are usually provided by the DSC instrument suppliers so that the instrument can be calibrated at respective time periods that are suggested by the suppliers. Sample preparation is a very important aspect in any analytical technique, and if the sample preparation is not correct, we may get results that can be misleading. The sample that is to be analyzed in the DSC should be representative of the total sample which you are trying to characterize. The sample weight for melting point is usually 3 to 5 milligrams. For the determination of TG or glass transition temperature of small molecule drugs, we take about 4 to 8 milligrams of sample, and for the polymers, we take about 4 to 8 milligrams of the sample. So as is clear, we require very small sample size to carry out the DSC analysis. Increasing the sample size will increase the sensitivity. For subtle events like the glass transition temperature, more sample size is required because the heat change involved at the glass transition temperature can be low, and to capture it, you may require a higher sample size. An optimum contact between sample and base of the pan that is used in the DSC should be ensured for proper transfer of heat from the furnace to the sample. And this is the right way of packing your sample in the DSC cell, while these two are not going to be the correct ways because the sample distribution is at the two corners here and only one corner here, while the heating is going to take place from the entire surface, and at some part there is no sample that is available for heating. So we have to be careful to ensure this kind of sample packing in the DSC cell. There are various types of DSC pans, and they can be made up of aluminum, copper, gold, platinum, and graphite. Aluminum is the most common material of construction, and the configuration of the pans could be either open pans, which can be further divided into pinhole or crimped pan, and hermetically sealed pan. So these are the pictures of an open pan. So this is a pinhole pan. This is a crimped pan, but here also you have some space for escape of the vapors, while hermetically sealed pans are airtight pans, and they are used for some specific type of experiments. In the open pans, sorbed moisture or solvent is evaporated during heating, and they are used to study thermal events without any interference from the sorbed liquid. While the hermetically sealed pans are perfectly closed systems, and they are used to observe effect of sorbed solvents on the thermal events. In the DSC, there is a continuous purging of a gas to maintain neutral atmospheric conditions in the DSC and to ensure uniform heat transfer in the sample cell. The most common gases that are used are nitrogen and helium, and the purge gas flow rate for nitrogen is 40 to 80 milliliters per minute, and for helium it is 20 to 30 milliliter per minute. The flow rate of the purge gas can have impact on the reading that we get. Too slow purge gas rate could lead to moisture accumulation and early aging of the cell, while too fast flow rate can lead to excessive noise during the recording of the signal. The temperature conditions that are usually used for the DSC experiments, we normally start from the room temperature, which is around 20 degrees Celsius, and we try to work in a range which is plus minus 20 from the anticipated temperature event of interest. Otherwise, you can start from 0 degrees Celsius or room temperature and heat it up to 300 degrees Celsius. This range covers almost all the transitions that are usually observed in the case of pharmaceutical samples. 10 or 20 degrees Celsius per minute is the heating rate for regular experiments, but you can use a slower heating rate as well to resolve the overlapping events. Here is one example of an overlapping event. You can see there is an event which is overlapped here. So there are two events, one this and one this one. And if you use a slower heating rate of 2.5 kelvins per minute, you are then able to resolve these two events. But if you use a higher heating rate, it will look like a single event only. So if you are observing a phenomena like this, you can use a slower heating rate to resolve these events into two separate events. The melting point of a compound is not affected by the heating rate because it is a first order thermodynamic transition, and this is an example where the melting point has been determined at various heating rates of 5, 10 and 20 degrees Celsius per minute. You can see at all the heating rates, the melting point is observed at the same value. As against that, glass transition temperature is affected by the heating rate that you use. And here is an example of amorphous celecoxib, where the glass transition temperature has been determined at 1, 2, 5, 10, 15 and 20 degrees Celsius per minute from top to bottom. As you can see, as you are increasing the heating rate, the glass transition temperature that is recorded by the DSC also changes. This means that while doing experiments related to glass transition temperature, all the experiments must be carried out at the same heating rate, because otherwise the values of the glass transition temperature are going to be different with different heating rates. Now we come to the applications of DSC in the pharmaceutical sciences. The first, most common or the simplest application is to find out the melting point of a compound. So this is a compound that has been heated from the room temperature, and it shows a melting endotherm at around 150 degrees Celsius. As I told you, in this DSC, the endothermic events are shown as a downward shift, while exothermic events are shown as a upward shift. In this particular heating curve, no exothermic event is being seen. So this is the solid sample as was viewed under the hot stage microscopy, and after the melting event, it has become molten. So this is the melting point determination using DSC. DSC can also give you the heat of fusion, which is obtained by integration of the area under this particular peak. We can characterize the polymorphic forms of APIs using DSC. Here is an example of indomethacin, which exists in alpha form and gamma form. This is the melting point of the alpha form, and this is the melting point of the gamma form. And this is the crystal lattice arrangement of alpha form, and this is for the gamma form. Since the crystal arrangement in the unit cell is different, that is why most of the polymorphic forms will show different melting points, and they can be recorded using a DSC equipment. Similarly, the polymorphic transitions can also be recorded using a DSC. So this is the hot stage microscopy photograph of a metastable polymorphic form, which will show a melting point at this temperature, followed by an exothermic event, which is due to the polymorphic transition. And then the new polymorphic form that has been generated will show its melting point. So the metastable polymorphic form first melts, then it recrystallizes to the stable form, and then later on the stable form will melt. So these kind of events can be very nicely captured using the differential scanning calorimeter. Hydrates and solvates contain water or solvent molecules in the crystal lattice apart from the API molecules. So this is a hydrate or a solvate sample, which will first show loss of the solvent or water from the crystal lattice, and this can be shown as evolution of bubbles from the samples. So bubbles like this can be seen due to the removal of the solvent from the crystal lattice, and then the melting point of the hydrate or the solvent will be displayed. Amorphous samples can be characterized for their glass transition temperature, and amorphous samples are those that lack the crystalline nature and have only a short range order of the molecules in their solid form. Amorphous systems are very popular because they can give you higher solubility and higher bioavailability. So they are used as an enabling technology for poorly water soluble drugs. But the downside of using the amorphous form is that the amorphous form is physically unstable and it can convert back to the crystalline form, which is the thermodynamically more stable form. So here is an example of amorphous celecoxib. So the first event that we see in the amorphous celecoxib is that of the glass transition temperature. You can see glass transition temperature is a very subtle event because it involves a very small change in the enthalpy or the specific heat. Thereafter, it enters into the supercooled liquid state. So this state is called as the glassy state. And after the glass transition temperature, it enters into the supercooled liquid state, which then shows recrystallization, which is an exothermic event. So you can see from the glassy state, you start getting the crystals. So there are birefringent patterns that are visible due to the needle-shaped crystals. And then finally, this crystalline form that has emerged will show a melting point. So this is an example of amorphous celecoxib, which shows all the events related to the amorphous form. Amorphous solid dispersions are formulated to stabilize the metastable or physically unstable amorphous form, and we include certain polymers into the formulation so that the amorphous API becomes more stable. Obviously, it is always very important to characterize your amorphous solid dispersion so that you can find out whether you have been successful in stabilizing the amorphous form of the API. Here, there are 3 DSC recordings. The first one is that for the amorphous drug. So here is the glass transition temperature of celecoxib. This is the recrystallization event, and this is the melting event that is subsequently shown by the recrystallized celecoxib. This is the glass transition temperature of the polymer, which is PVP-K30. This event is because of the water loss that is present in the polymer. And then later on, there is a very small event that has been shown by zooming in here. So this is the TG of the polymer. And the red line is the amorphous solid dispersion, which shows a TG value which is midway between that of the polymer and that of the drug. Depending upon the weight fraction of the polymer and the drug, this TG value will keep on changing. And we can also theoretically find out or calculate the expected TG value of the amorphous solid dispersion using Gordon-Taylor equation, and this is applicable for a binary system consisting of an amorphous drug and a polymer. So the predicted TG is given by this equation, where W is the weight fraction, TG is the glass transition temperature, and K is the ratio of free volume, which is given by this equation. Another very important application of the DSC and an extension of the conventional DSC is called as MDSC or MTDSC, which expands to modulated differential scanning calorimetry. This is also called as modulated temperature differential scanning calorimetry. The beauty of this technique is that it can help in separating the total heat flow curve into two parts, which depict the reversing events and the non-reversing events. What is done in the case of MDSC is that in a normal DSC, you heat the sample in a linear manner. So this dotted line shows you the heating curve. While in the case of the modulated DSC, the heating is provided in modulations. It is like a sine wave around the underlying heating rate. So the sample is being alternatively cooled and it is being heated, then again cooled, then again heated and again cooled. So a cycle like this is provided to the sample, and it helps in separating out the events that are recording into the DSC into the reversing events and the events that are non-reversing. Some of the reversing events of pharmaceutical importance are glass transition temperature, and melting can have both a component of reversing as well as non-reversing. And some of the non-reversing events are solvent loss, enthalpy relaxation, crystallization, and decomposition. So if there are two events that are getting overlapped in your normal conventional DSC, by using the modulated DSC, you can separate out those events to understand more deeply what is happening to your sample during the analysis in the DSC. We will see it with the help of an example in this slide. This is the total heating curve which was obtained for a sample. So this black color curve is the total heat flow. And there was an event here which could be glass transition temperature, or which could be water loss, or which could be enthalpy relaxation. Now in the conventional DSC, we are not able to understand that what is the exact composition or what are the exact contributors to this event. Using the modulated DSC, we were able to differentiate it into two components, the non-reversing event and the reversing event. So you can see the enthalpy relaxation came out in the non-reversing heat flow, while the glass transition temperature came out in the reversing heat flow. So here it was not possible to get the exact value of the TG, but in the reversing heat flow, you can get the accurate value of the glass transition temperature. So this is the total heat flow, and this blue colored are the non-reversing heat flow, and the red ones are the reversing heat flow. So this is done using an instrument called as modulated differential scanning calorimeter. Most of the DSC instruments that are supplied these days have the capacity to run the conventional DSC as well as the modulated DSC. So this was the glass transition temperature, and this was the enthalpy relaxation, as we have already discussed. Another very important application of the DSC in formulation development is to carry out the compatibility studies between the drug and the excipient. So here is an example of compatibility studies of rivaroxaban, and we have taken two excipients here, magnesium stearate and sodium lauryl sulfate. Rivaroxaban and magnesium stearate were mixed together and the signals in the DSC were recorded. Blue color is the heating curve for rivaroxaban alone. Red color is for the mixture of rivaroxaban and magnesium stearate, while the black color heating curve is for magnesium stearate alone. So you can see for rivaroxaban, we observed a melting point of 230 degrees Celsius, while in the mixture, the melting point was very close to 230, that is 229.62. This can help us in concluding that there is no major incompatibility between rivaroxaban and magnesium stearate. But look at the heating curves with sodium lauryl sulfate. So this is the melting point of rivaroxaban in the pure API sample, while in the mixture, this melting point shifted to a lower value of 213.97. which means there was a significant downward shift in the melting point of the drug. This is indicative of incompatibility between sodium lauryl sulfate and rivaroxaban. So using this as a tool, you can do a very rapid screening of the excipient for their compatibility with the API. Normally, the compatibility studies are carried out using the isothermal stress testing, where the drug, excipient, and the mixture of drug and excipient are stored at a particular temperature, like 40 degrees Celsius and 75% RH, and at different time points like 1 week, 2 weeks, 3 weeks, and 4 weeks. The samples are analyzed for assay value and physical attributes. So it takes about 4 weeks to get the data of the compatibility studies using isothermal stress testing, but the same data can be obtained using the DSC within a few hours. So that is the power of DSC, that they can give you very rapid indication of the compatibility between the drug and the excipients. However, there are certain limitations of doing compatibility studies using DSC, and we must be aware of them. The high temperature conditions that are involved in the DSC sometimes can lead to interactions that may never occur at the normal storage temperatures, which means the compatibility studies might show that there is an incompatibility in the DSC studies, but in the isothermal stress testing, you will not see any incompatibility. The second limitation of the DSC is that there is no participation of moisture while conducting the experiments, whereas in the isothermal stress testing, we always use moisture as a stressor while doing the compatibility studies. Presence of solid-solid interactions as shown by DSC does not necessarily indicate pharmaceutical incompatibility, which means there could be certain false positives that are shown by the DSC. Evaluation of the DSC tracings can be difficult, and the conclusions based on DSC results alone can often be misleading, because you will sometimes see a lot of transitions that are taking place, and it may not be able to interpret all those transitions carefully or nicely, and this could lead to certain misleading results from the compatibility studies. We can conclude that with respect to the compatibility studies, DSC is an alternative to the isothermal stress testing, but it cannot replace the classical way of carrying out the compatibility studies. Another very common application these days, since most of the research groups are working in the area of nano drug delivery systems or other enabling drug delivery systems, is the application of DSC in finding out the solid form of the API in your drug delivery system. For example, if you have generated PLGA nanoparticles of your drug, you would be interested in knowing the solid form of your API in the nanoparticles. Similarly, if you have generated self-nanoemulsifying drug delivery systems and converted it into a solid SNETs type of system, you will be interested in knowing whether your drug is in the crystalline form or the amorphous form or some other form. Here is an example of gliclazide, which shows a neat melting point at a temperature of around 172. Gliclazide plus Silicea 350, which is an adsorbent that is used for generation of the solid SNETs, shows a change in the melting behavior of gliclazide. This is the heating curve for self-nanoemulsifying powder, and this is the heating curve for self-nanoemulsifying drug delivery systems. We have to be very careful in interpreting these results, because what is coming out from this entire study is that gliclazide is not present in the crystalline form in the drug delivery system. What is the exact form of gliclazide cannot be commented, because we do not have any direct evidence about that. The only direct evidence that we have is that gliclazide is not there in the crystalline form, since you are not observing any sharp endothermic event in any of the peaks that are contributed by the drug delivery system. Similarly, the amorphous nature of the drug in lipid-based formulations can be confirmed by the absence of drug peak in the DSC heating curve of the SNETs formulation. Summarizing what we learned during this entire lecture, DSC measures the heat emerging out of a sample or consumed by a sample during the process as compared to the reference cell. There are two types of DSC instruments, heat flux and power compensated. DSC can measure a wide variety of thermal properties where sample preparation is subjected to the user application. First order events does not vary with change in the heating rate, while the second order events depend on the heating rate, and melting point is a first order event and glass transition temperature is a second order event. Pharmaceutical applications of DSC involves melting point determination, polymorph identification, characterization of the alternate solid forms, and drug excipient compatibility studies. So with this, we come to the end of our discussion, and I hope we have been able to highlight the important role differential scanning calorimetry plays as a thermal technique in the solid state characterization of pharmaceuticals. One important point that we need to keep in mind is, while doing the solid state characterization, we try to avoid use of only one technique for characterization. Which means if you are carrying out the DSC, it is most appropriate to use some other additional techniques for solid state characterization as well. For example, you can use one crystallographic technique like powder X-ray diffraction. You can use a microscopic technique like polarized light microscope. You can use a spectroscopic technique like FTIR or Raman, in addition to the DSC findings that you have got for your sample. So an array of solid state characterization techniques helps you in getting useful information about your sample and the events that are taking place in the sample. Thank you very much. If you have any questions, I will be very happy to answer them. Later on, also you can write to me on the email ID akbansal@nipper.ac.in for any clarifications that you want to have. Thank you very much for your attention.